On December 21, 2022, Winter Storm Elliott crossed the United States. Every major airline took the hit. Within 48 hours, United, Delta, and American were running again. Southwest was not. Over 16,900 flights canceled, 2 million passengers stranded, more than $1 billion in losses. The weather had cleared. The schedule had not. This was not a weather failure. It was a computational failure. Southwest's scheduler, a legacy system known internally as SkySolver, was running, but it was optimizing a phantom airline. The state inside the computer was hours out of date. Static solvers, faced with combinatorial explosion, do not gracefully degrade. They collapse. The fix is not a chatbot that explains a schedule. It is an agent that repairs one. Crew scheduling is a set partitioning problem, NP-hard. For a major airline with 4,000 daily flights, the number of legal crew pairings is effectively infinite. Operations research solves it with column generation, a 30 to 60-minute optimization cycle that produces a beautiful schedule for a frozen world. But during the meltdown, the world was not frozen. Cancellations changed the problem definition every 5 minutes. The solver was always one cycle behind reality. This is the optimization execution gap, and no chatbot wrapped over a failing solver can talk it out of the trap. The bottleneck is not the interface. It is the reasoning. Veriprajna's answer is graph reinforcement learning. Stage 1. A graph attention network encodes the operation as nodes and edges. Airports are nodes. Flights are edges. Every node carries a high-dimensional embedding, pilot fatigue, maintenance status, weather risk. When a blizzard closes Denver, the embedding for that node updates, and through message passing the risk signal propagates to every connected node. A pilot in Baltimore preparing to fly into Denver receives the disruption signal in their embedding before they even depart. Stage 2. A multi-agent reinforcement learning policy. The action space is operational. Swap crew, cancel flight, delay departure, deadhead. The reward function is shaped by business goals. Cancellations, delay, and crew overtime are all penalized. Trained with proximal policy optimization across millions of synthetic crises, the agent maximizes long-horizon value, not local efficiency. It learns strategic sacrifice, cancel a flight today to save 10 flights tomorrow. Stage 3. The neuro-symbolic sandwich. The neural network proposes a probability distribution over actions. A symbolic constraint engine, encoding FA Part 117, union contracts and maintenance rules, applies a mask. Any action that violates a hard constraint has its probability set to 0. The agent cannot execute an illegal action, ever. Stage 4. The digital twin. Agents do not train on a live airline. They train on a state transition engine that simulates 10,000 years of operations in a week. Stochastic generators inject superstorms, mechanical groundings, and labor strikes. By deployment, the agent has lived through more meltdowns than any human dispatcher. We reran the December 2022 crisis inside our digital twin. The legacy solver fed the same lagging data, choked on the cascade. Recovery time, 7 days. Our graph reinforcement learning agent saw the point-to-point fracture emerging in Denver hours before the wider network noticed. It executed a preemptive firewall, canceled 20% of inbound Denver flights early. Deadhead crews to Phoenix to create a secondary operational base. The disruption was contained. Total cancellations were reduced by 66%. The East Coast network remained 95% operational. The same architecture is being adapted across logistics. In maritime, anchorage and terminal agents renegotiate berth slots and truck appointments in real time as vessels arrive late. In rail dispatching, the agents learn to hold a freight train early to clear a path for an express train 50 miles upstream. A non-intuitive policy that outperforms human dispatchers and first-in first-out heuristics by 15 to 20% in delay reduction. The wrapper era of enterprise AI is a coat of paint on a seizing engine. A chatbot over a legacy solver does not reason. It merely interfaces with a system that already failed. The engine alternative, graph reinforcement learning, trained inside a digital twin, gated by neuro-symbolic constraints, delivers 2 to 5% operational savings in normal weeks and survival in catastrophic ones. Southwest lost $1.2 billion in 7 days. That single event erased years of efficiency gains from running a lean network. The tail risk is no longer a footnote. It is the dominant cost driver. The future belongs to those who can reason, not just those who can speak. Veriprajna engineers true intelligence for the systems that move the world. Read the 17-page technical brief, about 25 minutes of your time. The math, the architecture, the case studies, every claim grounded in the work.